Hello and welcome to this video tutorial for problems 8 through 10 on your 8th homework assignment. We are given in this particular problem a stress element that has the following stresses. In this case, it's 7 KSI for sigma XX. For the sigma YY face, it is 22 KSI. Both of these are tensile, so they're positive. And once again, we have negative shear of tau xy equals negative 6 KSI. And what we want to do is we want to find the orientation of the planes of maximum and plane shear stress and figure out what the maximum shear stress is. We also want to know the normal stress on the element at the maximum shear orientation. So there are a couple of potentially useful equations that you could use to solve this problem, and they would result in almost one-liners. If you have access to them, great. If you memorize them, great. But there's absolutely no need to memorize these equations. So you would have tangent of 2 theta s, the orientation of the maximum shear plane, equal to negative sigma x minus sigma y over 2 tau xy, and that would be equal to negative 7 ksi minus 22 ksi over 2 times negative 6, or negative 1.2500 for theta for tangent of 2 theta s. Of course, when I solve for theta s, I would end up with theta s equals negative 25.67 degrees plus or minus 90 degrees. Well, that means that I've got two shear planes that would be maximum shear. One plane looks like this, the other plane looks like that on the rotated element. So you would rotate the element by the angle theta p, and then the shear plane would be at 45 degrees more than what you would rotate this element to get it into its principal orientation. Of course, with tau max, we have sigma x minus sigma y over 2 quantity squared plus tau x y squared, all under the square root. And that gives us 9.60 KSI. So, like I said, these are great if you have them memorized, if you can look them up. However, there's no need to do that. There's no need to memorize any of that because it can all be figured out through Moore's circle. And what we would do is we would plot for the x point, it would be positive 7 and positive 6. So that would be sigma x and negative tau xy, and I would plot 7, 6. And then for sigma y, for the y face, I would have sigma y of positive 22, and tau xy was negative 6. So that actually matches the sign convention for the element for the y face always. And then the x face would just be opposite. So we've got the diameter constructed by drawing the line between these 2 points. The average stress is 14.5 KSI. And this angle here is 2 theta shear. So tangent of 2 theta shear is equal to 7.5 over 6. And that gives me 2 theta shear of 51.34, or theta shear of 25.67 degrees. But notice I have to spin the diameter clockwise, and that's a negative angle. So your book is going to call that answer negative 25.67 plus or minus 90 degrees, and it'll probably want the smallest negative angle, the smallest positive angle. So for that one, we're going to take theta shear right here, or we would just rotate like that. through 2 theta s. And since it's a clockwise rotation, it's a negative angle. So for the other one, for the counterclockwise one, it would be this angle through here. And this would also be 2 theta s. So you would have negative 25.67 plus 90 degrees. So you also want to know what the normal stress is on all elements when you get to the rotation where you have maximum shear stress. Well, that just ends up being sigma average, sigma x plus sigma y over 2, because they all of these points of interest lie on the same vertical line, which passes through the midpoint of the circle, which goes through sigma average. So in this case, it would be 14.5 KSI. So that's how we would deal with maximum in-plane shear and the orientation of the maximum shear planes.